Hello, I'm Shankar Guha. If you haven't been living on another planet for the last 5 months, you'll be fully aware of the nightmare scenario of a deadly virus spreading from distant countries. I'm talking about Ebola. The chances of being infected by this particular virus remain, thankfully, unlikely. However, many scientists now believe that a lethal global pandemic is inevitable. No question in their minds whether it'll happen, so much as when it'll break out. In today's episode of Bursts, we'll see how easy it is for an infectious flu virus to spread in the modern world, from right here in London to Budapest, and from there to all corners of the world.
Albert László Borabashi, a Hungarian scientist based in Boston and Budapest, is a world authority in network science. His discoveries have inspired research in numerous other fields, such as pharmaceutical drugs, social networks, and corporate restructuring. His recent book, Bursts, investigates whether universal laws or principles underpin all human behavior, and if such principles do indeed exist, what use are they to us? Is it possible, for example, to use these laws to work out what any given individual will do in future? On today's show, we'll look at how viruses spread through time and physical space. Harry is a 25-year-old Hungarian banker who works in London. He's getting married in 2 days' time. He's chosen to have his stag party in Budapest. His friends are jetting in from all over the world: Barcelona, Buenos Aires, Singapore, and New York. He's suffering a minor headache and a bit of a cough. He doesn't give the symptoms a second thought. He doesn't know it yet, but at his upcoming wedding in London, he'll pass on a highly contagious flu virus to his new mother-in-law. This is Daniel, one of Harry's closest friends. He's in charge of organising the party. As part of the fun and games, he's compiled a list of silly challenges for the groom-to-be. The next task Harry has been set is to cut out the washing instruction label from the underwear of as many women as he can persuade to play along. Best of luck, Harry.
Harry doesn't know it yet, but since he arrived in Budapest, he's picked up a flu virus, which he'll unfortunately be taking home to London with him tomorrow night after his bachelor party. His early symptoms are beginning to appear, but the full fever will take 24 hours to develop. In the meantime, I'm going to do some research to find out how quickly a virus can spread, how many people it can affect along the way, and how far it can travel.
Recently, in 2014, the Ebola virus struck fear across the world. Near panic has set in. Borders have been shut and high-risk people have been quarantined. The aim is to stop the virus travelling. And so, understanding how and where people travel is vital to understanding how a virus like Ebola spreads.
We've had quite a lot of health scares, haven't we? We've had bird flu, SARS, we've got Ebola now, HIV, going back a few decades. Is that all they are, scares?
Well, I don't think we've seen everything yet. In a way that in the 21st century, the question is not whether we're going to have a big, deadly epidemic, but when we're going to have it and how that is going to be. And what we need to realize is the answer will not be medical, because it takes months to years to develop a vaccine or a cure to a new disease. The only way we can stop a future deadly epidemic is to understand human mobility, because we have to stop it in its tracks.
So your research is not just an academic hobby. I mean, there's a real serious outcome.
One of the biggest application area of understanding human mobility is to where would viruses spread and what can we do to effectively stop it without killing the economy at the same time.
So Harry will come down with a full-blown fever tomorrow night. My next job is to try and figure out how many people he could pass the virus to, and how they in turn could pass it on. Coincidentally, this is exactly what scientists do when they map the worldwide spread of viruses. Hey Harry, how's it going?
Best night ever, mate.
Cool.
Alessandro Vespignani is a professor of physics, computer science and health sciences at Northeastern University in Boston. Professor Vespignani is known for his work on complex networks, and in particular for his work on the applications of network theory to the spread of disease.
Well, Ebola was a disease that we used to think was confined to remote regions of Africa, and we never experienced a very large outbreaks of that disease. The current 2014 outbreak is probably the most dangerous that we have experienced. And it's really a kind of evidence of how much we are all connected now. Epidemics are without borders. Although those regions are not very well connected to the outside world, however, the epidemics has reached the major cities and transportation hubs. And at this point, there is an appreciable probability that somebody was being exposed to the disease and is just in the incubation period, will be on a plane with a destination to a European cities or in the United States or any other place. So far we find that the probability of the international spread is rather small, although not negligible. So we have to be ready to see cases of Ebola imported in countries around the world.
Today, viruses can travel great distances with their human hosts very rapidly. Back in the 14th century, the plague, or Black Death as it came to be known, could only be spread by foot or on horseback. Nevertheless, it conquered Europe, wiping out 30 to 60% of the population over decades as it moved in a slow wave from village to village.
Harry has a new challenge. He has to collect money from passing strangers by doing whatever they ask of him in exchange for their loose change. Most are happy to pay him to go away, but as long as he gets a few coins, it all counts. In the process, Harry, who's carrying the flu bug, will probably infect 10 more people.
Hollywood movie fans are already familiar with storylines in which a Matt Damon or a Dustin Hoffman save the world from a deadly virus originating in a faraway country. If only real life was as simple as the movies. In the real world, scientists are battling to come up with complex mathematical formulas that can accurately predict how a virus spreads and how it can be stopped.
Dirk Brockmann is a theoretical physicist currently at Humboldt University in Berlin. He's best known for his work on computational epidemiology and a study investigating the geographic circulation of dollar bills in the United States.
So one of the most important challenges in epidemic control is finding the outbreak source. The source could be a patient, the first person that contracted the disease, or the location, the geographic location where it all started.
Did she mention seeing anyone who was sick? Anyone on a plane at the airport?
No, she said she was jet lagged.
The average person touches their face 3 to 5 times every waking minute. In between, we're touching doorknobs, water fountains, and each other.
Matt, no, go up to your room, honey.
To the best of my knowledge, I'm not bringing a virus with me on this visit to New York, but it's possible the kids around here might appreciate a couple of days off school if I was. But let's return to our theme. If we understand how people travel, do we really get any closer to understanding the spread of viruses?
When trying to predict the spread of contagious diseases in the modern world, scientists have to face new challenges that have arisen since the time of the Great Plague. Because the invention of cars and aeroplanes means that people are traveling much faster and further than ever before.
One of the things that we had to understand is human mobility. How do people move? So we had to measure human mobility. One perfect solution for this seemed to be a website called where'sgeorge.com, which instead of tracking humans, tracked the movement of individual dollar bills.
To recap now, this is how the Where's George website works. The current owner of a particular dollar bill enters the serial number of that note on the site, as well as their own postcode. The site is then able to calculate the GPS coordinates of the dollar bill at that moment. Then the owner of the bill stamps or writes the Where's George web address on the note before spending it.
The next owner of the dollar can visit the Where's George website, update the marked bill's latest location, and also see where it's been.
When we looked at the Where's George data, the movement of individual dollar bills, we found something very intriguing. The distances between individual finds did not follow the Gaussian shape by Einstein's theory. Instead, they followed a power law distribution. So this was a very important find and had enormous consequences. However, the individual movement of dollar bills was not identical to movement patterns of individual human beings. So something was still missing in the big picture.
Harry's latest task is even sillier. He has to persuade people to give him their socks.
I'm sorry. I need my socks more than you need.
No way. Well, Harry's 5 minutes are up and I've managed to hang on to my socks. But as you can see, he has been successful in collecting 8 pairs from others in this bar. When he returns those socks, he may well be infecting 8 more people. Anyway, Harry and his friends are pretty smashed now, and I don't suppose they care. Time for a quick snack. Show us your socks.
In taking that snap, I unconsciously revealed both Harry's and my exact location to the mobile phone company. From this data, our movement patterns can be analysed.
And of course, as soon as I switch on my phone, somewhere out there, my precise location has been logged. But you may be wondering, what has this got to do with the spread of viruses?
It has a lot to do with it, indeed. Tracking the movement of dollar bills does not reveal how far each person goes. However, mobile phone data can provide answers to that question. The signals sent from a handset to the transmission towers can be examined in real time to determine how far the owner has traveled. Marta Gonzalez is an associate professor at the Massachusetts Institute of Technology in Boston. She analyzes vast data sets on human activities and uses them to formulate models on the underlying patterns of human behavior. Her conclusions are useful to town planners making decisions on mass transit systems and energy policy.
I have worked with user data of more than 100,000 mobile phones. My observation suggests that most people do not get swept off to long-distance places. For the majority, mobility means a well-defined limit number of locations.
This girl, obliging Harry with his lipstick challenge, is no exception to the rules of mobility. The likely locations she'll visit in a given year follow a well-established pattern. Once a year, she travels on holiday to a beach somewhere hot. In winter, she visits her parents in the country at Christmas. Most of her time, however, is spent close to home in her neighborhood, where, after work, she and her friends are regulars in various bars. Most people tend to move within a 3-kilometer radius on a daily basis. A smaller but sizable group move within a 15-kilometer radius. An even smaller proportion travel 75 kilometers. However, there are some extreme exceptions. Individuals who routinely travel hundreds of kilometers every day.
Coming up, devastating pandemics have been with us throughout history. But since we've been able to transport viruses with us from one continent to another in a matter of hours, the danger they pose to us all has become much greater. These days, the deadliest virus can travel from its point of origin to many destinations around the world simultaneously at the speed of a jet plane. And so scientists are racing against time to be able to identify potential threats at source and map the possible ways they might spread across continents. We'll be hearing from a leading expert on the subject shortly. Welcome back. we know that leading researchers into viruses are saying that a global pandemic is inevitable in the 21st century. They've reached this conclusion because of the speed at which humans can now travel around the world as a result of 20th century innovations such as motor vehicles and air travel. Once it's been established how the virus carriers, that's to say human beings, move around, that information can be put to work. In this day and age, of course, the primary form of travel is by air, so mapping people's flight patterns is the key to predicting how viruses spread.
So human movement as such is very important in taking viruses from one place to another. But that's very different nowadays than from, say, a couple of hundred years ago. Nowadays, say there's a virus outbreak in Manhattan. In a matter of days, it can get to London, which is a place that is very far away, but there's lots of traffic to London, as compared to, for instance, some small village in upstate New York. So the geographic distance is no longer a good measure for how long something will take a virus to go from one place to another.
Aaron Koblin is an American digital media artist who uses real-time flight data to create works of video art like this one. It also serves as a scientific illustration of global travel patterns and demonstrates how quickly and easily a virus can travel across continents carried by human hosts. These patterns of movement can be analyzed and used to forecast the likely spread of epidemics. The H1N1 swine flu virus was the first global epidemic that scientists successfully created a model for. They predicted the speed at which the virus would spread, what routes it would take, when it would peak, and when it would die down. Scientists based their predictions on mobile phone and air travel data.
What the model produces is the where, when, and how. So basically we are trying to see which places will be affected by the disease, when, and how much. We can really follow microscopically 6.5 billion individuals. We can see which flight they were on spreading the infection. So we can create realizations of each epidemic. Obviously, what we do is to create a portfolio of those possible evolution and look at the statistical more likely patterns to occur. So we find statistical indicators that allow us to make projections and look into the future.
Let's return to Harry. He's collected an impressive 32 lipstick imprints on his shirt. And as he's kissed all 32 of the women who obliged him, they're all potentially infected by him. He's on his way back to the airport to catch the flight to London now, along with his friends and a married couple seated behind him. All of them are now at risk of catching the virus. The chances are high that this merry band of friends will in turn become carriers of the virus. Finding the source of an epidemic is like finding the source of a water ripple. But pathogens don't spread across the world in neat ripples. The challenge for scientists is to identify the appropriate ripples in the underlying patterns of human mobility.
When you look at the spread of a pandemic nowadays, for instance H1N1 in 2009, it spreads like a circle, but it's no longer the geographic distance that shapes the circle, but it's the time. In fact, when you look at the pattern of H1N1, it looks very complicated on a regular map. So when you use, instead of geographic distance and effective distance, the complicated pattern becomes simple again. And the arrival time of H1N1 in some location on the globe correlates very well with this new type of effective distance.
How viruses spread among humans is one thing, but we often talk about computer viruses, and we also use the word viral to describe how internet memes spread. That's no accident, because viruses, human or computer, follow similar patterns.
The word meme is derived from the Greek word mimema, meaning imitation. Memes are packages of condensed information, often taking the form of an amusing image, a video, or a caricature. Thanks to the creativity of internet users, thousands of new memes are posted every day. The most popular memes replicate across the network at incredible speed and mutate into uncountable new versions. Sinan Arol is a professor of management at MIT in Boston. He's a world authority on social networks, social media, and digital strategy.
Ideas and behaviors can spread from person to person, and they're similar to viruses because we tend to spread them to people we know. We have to have contact with them, and we have a sharing of ideas or of a communication, and we can trace these ideas as they move in the network through email or through Facebook messages or Twitter. And so this way we see that they're spreading from person to person along a social network path. People who know one another, people who trust one another. The basic idea is that if we understand how ideas and behaviors spread and understand the dynamics of this, then we can learn how to make messages go viral or to change population scale behavior. Let's say you want to promote the adoption of solar cells as a renewable energy source. You can use this kind of information to generate the spread of a behavior like adoption of solar cells.
There are many kinds of mobile phone viruses, but not all of them spread as far, like email viruses. Bluetooth viruses, for example, spread by proximity of devices, much more like human viruses.
Daniel happens to have been vaccinated against flu and so avoids being infected by Harry. So he's lucky. But with global epidemics, it's best not to trust to luck. Knowing how viruses spread isn't enough in itself to contain global epidemics. It's also essential to know how to effectively immunize a population. Shlomo Havlin is a professor of physics at Bar Ilan University in Israel. His research into complex networks focuses on optimizing the stability of networks such as the internet against deliberate attacks and viruses.
A good method, which was already noted in the year 2000, is of course to immunize the high degree, the hubs. If you immunize all hubs, then you can stop the propagation of the disease. But usually in people you don't know who is a hub and who is not. So there are many ways that were suggested during the last 15 years how to immunize best. One way is we call it acquaintance immunization. Means that you don't immunize random people, but you immunize their friends. Everyone, random people, you ask random, give me a name of your friend. And then if you immunize the friend, usually the friend has more connections than you, and you immunize them, then you can stop the spreading of the disease. Another way is to break the network into clusters of same size, to immunize the boundaries of these clusters. If you immunize the boundaries, you can stop with very few doses of vaccines the spreading of the network.
Does your research specifically help us to understand epidemics?
To really understand and stop an epidemic, we need to understand where and when it spreads, which means that we need to understand the network on which it spreads between the individuals and the timing of each event, which means we must understand bursts.
Okay, so these are your two big theories.
That's right. That's exactly what we need, networks and burst theory.
Each epidemic has what we call the patient zero, so the first guy that gets the epidemics. Now, the Harry, your character, is actually not the patient zero because he got the infection somewhere during this trial. So probably he has been in contact with somebody who was already sick or transmitting the disease. As every person that is infected with a new strain of a disease, Harry is a real threat, as well as a real threat all the people that have been in contact to him. Diseases always tend to have this progression. They will start in some place. From there, they will navigate to a major hub, like London, Paris, New York, those major cities, Singapore, wherever. And then from there, they will start to infect the other hubs. So these are the most likely elements of the system that will get infection because they get a lot of passengers. They get more transfer passengers as well as destination passengers. And the epidemics will unfold this way, going from hub to hub and then, cascading through smaller airports, smaller cities, smaller geographical regions. And these are according to pathways that we can measure and model so that we can have an understanding of what will be the future unfolding of the disease.
Following the stag party, Harry returns to London with happy memories. But within 24 hours, he's already passed on the virus to dozens in Budapest and will continue infecting at least 250 fellow travelers and guests at his upcoming wedding. They in turn will become virus carriers. On such an exponential growth curve, the virus will be an epidemic within days.
And now, just 2 days after Harry's bachelor party in Budapest, he's indirectly infected people as far afield as Barcelona, Boston, Buenos Aires, and right here in New York. In his recent book, Bursts, Professor Borobashi reveals that many aspects of our future are indeed predictable. So, should we be scared of the implications? If we care about our privacy, do we have any choice other than to abandon our digital devices and go live on a desert island? Recent revelations by whistleblowers have revealed the extent of the digital footprint we make and how it's being monitored secretly by governments. But it doesn't have to be that way. Rather than being fearful, I prefer to be an optimist. If we can come up with the right checks and balances on those who want to limit our liberties, making our data accessible to researchers can deliver great benefits for all of us. I'm Shankar Guha. Thank you for joining me on this journey into the future.